we continue. So I repeat almost everything I did yesterday in a faster pace. So, which was structure of the standard model Lagrangian, and then we'll go ahead and try to see how masses are given to particles. So let's see what we do. So this was a refinement of the standard model Lagrangian, which finally looks like this. It has many parts. And now that we have seen yesterday's class, we know what all these lines are. Okay. So to remind you again, first line is the kinetic term for the gauge bosons, is B and 3 Ws. Then the second line gives you the modified kinetic term for the left-handed fields. So all these L's are doublets of fermions. Each L consists of 2 fermions. Okay. And we saw that there were 12 such. Then this is the right-handed fields. Okay. Each of them with a singlet. So this is not a doublet. This is only one fermion. Okay. This is the modified kinetic term for fermions. And there are 21 listed. This part, the green part, gives the Higgs term. So this 5 is the Higgs doublet. That's again doublet, so it has 2 complex scalar fields. This is the modified kinetic term. It's like del mu phi mod square. And this is the potential. The rho of potential is something that we will see today. And then we have got this term below here, which again we will talk about today. These are Rickow coupling terms, which will end up giving masses to all the quarks and electrons.
Generally saying, if there was it's a boson, then it will appear in the Lagrangian square of the del mu term. And for fermions, it's first order. All fermions, it's first order.
It should be. See, it's like this. No? From the Lagrangian, you know how to get equation of motion. Equation of motion for boson is a time-ordered equation. Okay. So therefore, you can get time-ordered equation only when you start with the square, so 2 derivative.
So no matter what we do, we just need to know whether it's a fermion or a boson to put in the kinetic.
Yes, that's it. See, Lagrangian is in some sense what you get by some trial and error in theory. Because you know what is the equation of motion. And then you figure out what Lagrangian is and that it suits. Then if it has some nice canonical form, then you are glad that you are also fitting in some place. Yeah, so boson, it's del mu phi minus m square phi square.
But a line modification has a bigger domain, right? It's satisfied by both fermions and bosons. And Dirac equation is only satisfied by both.
Yeah, that's true. So this will give you Dirac equation for fermions, which implies that it also gives time order for fermions. So fermions to satisfy the most stringent constraint. Most stringent constraint is Dirac equation. So if this gives the Dirac equation, it automatically gives you.
In limit, we can go from Dirac equation to Lagrangian equation.
Well, not limit, but yeah, Dirac equation implies time order.
Also satisfied.
Also, right. Therefore, Dirac is the most stringent constraint. So satisfy Dirac and then. Okay. So fermions you need to satisfy Dirac also. So once you do that, your time order comes. Then what we do is we try to construct this Lagrangian step by step. Okay. By starting with only fermions and Higgs, but no gauge interactions. Okay. So therefore, we only had this L bar, gamma mu, del mu L, and R bar, gamma mu, del mu R, and this is I del mu phi square minus C. This is the Lagrangian when there are no gauge terms. Okay. So fermions, left-handed fermions do something by themselves, right-handed fermions do something by themselves. Higgs does something by itself, and none of these three at all interact. So this is what would happen if you don't have Higgs. Then we say that we want a Lagrangian which has some gauge symmetry. Okay, so for example, this Q1 pi. The gauge symmetry would mean that if I apply a transformation on this field psi like this is essentially changing the phase. This is a parameterization. So this is G prime by 2 is a coupling constant. Alpha is some function which can be anything all over space. and 1 is the hypercharge of this. And then, as you have seen many times before, only this transformation would not keep our simple Lagrangian invariant. Along with this transformation, you will have to change your derivative to this del mu plus some I is equal to d mu y, where this d mu is now a new auxiliary field, which also should change under this gauge transformation as is. So if you apply 1, 2 and 3 simultaneously, then the Lagrangian is invariant under U1, and then so what you have done is, by imposing this U1 symmetry, you have actually predicted what the Lagrangian is going to do. So I didn't give you anything extra. I just told you that you have to do this U1, and that actually tells you what the Lagrangian is. I didn't have to tell you any extra information. All I need to tell you is perhaps what are the Y eigenvalues of all these fields. So that's something that you will get by experiments and not by theory. Your many particles, primarily if I give you a new particle, you will have no clue as to what its Y value is. Of course, if it fits into some pattern, then yes. Okay. So for example, if you're thinking, oh, we had electron, before electron neutrino, and of course we know that Y values of electron should be same as that of electron neutrino. In that case, yes, we know what it is. But if I randomly give you a new particle, the only way for you to find out its Y value is by doing an experiment. So, Y eigenvalues are this. I gave you a list. The only thing to note is that when you have a doublet, it's infinite doublets, both of them are going to have the same Y eigenvalues. So, in addition to these three, this new gauge boson d mu has two properties. Firstly, it can have no mass term, because if it has mass term, then you have b mu kind of term, and if you have this transformation, then you can't do anything about it. The term will not remain invariant under gauge transformation. So therefore, gauge symmetry tells you that you cannot have a mass term for this b gauge. Secondly, now this b gauge boson is a particle, it must have a kinetic term. Kinetic term normally look like kinetic term normally will look like del mu b mu or square. That's sort of boson kinetic term. But we already know that we don't only need this term, but we also need to have term which satisfies this U1 symmetry. So which means that under this transformation, d mu going to d mu minus constants g prime by 2 times del mu alpha. The kinetic term also should not change. So therefore, this kind of term looks bad. However, if you look at something which looks like this, del mu d mu minus del mu d mu, it's also kinetic square. So let's look at this term. This is the first derivative. Now, if you look at this term, and if you see what happens to this term under this gauge transformation, see what happens. So this becomes we add this will become del mu minus g prime by 2 del mu alpha du went to du minus g prime by 2 del mu alpha. And the second term is minus, this is del mu du minus g prime by 2 del mu del mu. And now you see that because I have this reverse subtraction, these extra terms actually drop. Okay, as a result, under gauge transformation, my del mu du minus del mu du remains the same. And this is what is defined as B mu. So B mu is a quantity which is like the first derivative of B, which is invariant under this B. Okay, so now this is a good quantity. And therefore, the square of this quantity, or strictly speaking, B mu nu times B mu nu, now acts as a good kinetic. So now if you take this term in Lagrangian, so this has minus 1/4 in front of normalization. But now if you take this term in the Lagrangian, and if you try to find out what is the equation of motion, you will see that it is just gang out the equation of motion for the wave. Maybe this is a good thing to give you in the assignment. So it's a good thing to check. So therefore, when you added U1, all we have done is have these three conditions and add this kinetic. That's what you see here. So all we have done is added these red terms. So you get a kinetic term here, and all three derivatives here get modified through this G prime by 2 times E. Right? Then we do the same thing with SU12. SU12 again means that I need my psi to transform like this. Okay. So remember, this psi is a doublet. And that implies that we have a gauge field W, 3 gauge fields actually, and these three conditions. Let me, so I talk about this just a moment. Whereas, why eigenvalues are rather difficult to imagine. It's very easy to imagine the SU2 eigenvalues. You always know the left-handed objects come in doublets, right-handed objects come in singlets. Whenever you have a doublet, it's a doublet of isospin, G isospin, so T is equal to half, and upper component has T3 equal to plus half, lower component has T3 equal to minus half. So SU2 eigenvalues are other straightforward. For doublets, upper part has plus half, lower part has minus half, and all the original objects have zeros. So that's how it's straightforward. Again, all these W's cannot have mass term, again for the same reason that you can't have a gauge invariant mass term. Okay. And you have a kinetic term, again looks like W mu W mu. Okay. However, this W mu is slightly different from our B mu. So for B mu, we saw that if you do this, then these terms cancel out. Okay. If you try writing down only del mu W mu minus del mu W mu in this form, these things won't cancel out because W's don't W. So you will have problems. Right now, just take it from me that if in addition to these terms, you also added this extra term, then cancellation will be good. Okay. So again, I will tell you to better exercise. You see that is cancellation. Now, once you have this object W mu, which is gauge invariant also, then you can square the object, and that will be kinetic energy. If proper coefficient, which is minus 1/4, the term will therefore be W mu dot term. This is what we got. We added this term, W mu, we added this term here. R did not get the term because all the R fields had isospin equal to 0. And even for phi, since phi is also a doublet, phi plus phi 0, you get this. So this is the Lagrangian that we have through gauge. I wanted to make one point which I did make yesterday, which is the following. So this is not just simple mathematics, it also tells you something about physics or complete concepts. So what is that? So let's say, look at this term. This is L bar, gamma mu, W dot tau times L. So let's look at this term and see what this term actually looks like. So we had a term that was L bar, gamma mu, then I had minus G by 2, minus G by 2, then I had this W mu dot tau let's see what this term tells us about interactions. Let's see what this term actually. So we are dealing with Neutrino, so let's take a simple L, which is UE. So let's see what is term. So let me put this minus G by 2 here. L bar would be U E bar E bar. This is dagger times gamma 0. So, E bar. Then there will be a gamma mu, but let me forget about mu for a moment. That is mu is Dirac index, right? It's not doesn't fall in this case. Okay, so let's forget about gamma. So I just want to now write W dot tau times L. L is again. So what is this W dot tau? What? Yeah. So okay, just see W is a vector which is a W1, W2, W3. So this W dot tau is nothing but something like W1 tau 1 plus W2 tau 2 plus W3 tau a sigma matrices. So let's try to expand this and see what it is. So this minus G by 2, right? This is U E bar. So then I will write it as W1 tau 1 times plus U E bar W2 tau 2 times plus this actually stands for this correspondence. Okay. So let me write that down. W1. Let me actually simplify things a bit. So let's write this down in a different way. So we know what is tau 1. Tau 1 is sigma 1, so that's 1 1 plus W2, which is 0 minus I 0 plus W3, tau 3 is 1 minus 1. Okay, so this essentially looks like W1 minus I W2. W1 plus I W2 0 0 plus W3 minus W1 minus I W2 is defined as omega plus times root. This is definition. So not omega W plus. So this by definition is 1 by root 2 times another omega. So times this is defined as W plus and this is defined as W plus. I'll tell you what is that is what this means, because the reason this has been done is such that see we also have this tau plus and tau minus. So tau plus is defined as tau 1 minus I tau 2. I think it's minus. I correct the sign. So tau plus therefore is 0 1 0. plus I times tau 2. So this is 1. This is minus 1, 0, 0. And there is a 1 by root 2. So this will be root 2 times 0, 1, 0. Okay, I guess there is no. So now if you look at this and this, you can see that I have actually been able to write these things as W plus tau plus. Similarly, tau minus is going to have a 1 here and a 0 here. So plus W minus tau minus plus so let me go back a bit. So instead of writing down this as W1 tau 1, I write as W plus tau plus. Let me just write this down now again in the next.
When you start looking at these as isoscale breathing and lower.
Yes. So that's exactly what it is. So V bar, W plus tau plus W minus tau minus plus W tau 3. Okay, so therefore I have 3 terms. So let's see what these terms are. So I put this minus G by 2. So first term is U E bar W plus tau plus times nu E bar. Tau plus we saw was 0, 1, 0, 0 times nu E. The second term is U E bar W minus 0, 0, 1, 0 times. Third term is again U E bar W3 1 minus 1 times. So let's see what this becomes. 0, 1, 0, 0 would mean 0 E. So this is U E bar W plus 0 E E0. Sorry. 0 plus U E bar W minus how is it? 0 U E 0 U plus U E bar W3 times 2E minus. Okay, so this way. So what does this give me? This gives me U E bar W plus E. Okay. Second term gives me E bar W minus U E. Third term gives me U E bar W3 U E minus E bar W3. So what have we done? This compact Lagrangian that we were looking at earlier, we expanded it by this. Remember there is a minus G by 2 outside. Okay, so let me bring it down. That's minus G by 2 which multiplies this whole thing. So what does this mean? This means that I have got a vertex which is the nu D bar W plus electron. Okay, which means a vertex with electron coming in minus W plus coming in and a UV going out. Bars corresponds to going out. So this tells me that my theory has this vertex. And this vertex has a strength which is equal to there's a minus G by 2. Okay. And now remember things that we have forgotten. Okay, so we had forgotten the gamma mu. And to be precise, this W will come. So I just put in all the indices that we had ignored. So this tells that our theory, if you have draw Feynman diagram, you can draw Feynman diagram with electron and W combining to give you electron neutrino. And the coupling constant is minus G by 2 gamma. This term tells me that I can have a neutrino coming in, so nu E coming in. I can have a W minus coming in and have an electron going out. And this strength is also equal to the same. So minus G by 2 times gamma. This tells me that I got vertices that look like nu E coming in, coming in, nu E going out, and W free mu coming in. Similarly, electron, W3. And I also know what the string theory is. The string theory is again minus G by 2 gamma mu. And the string theory is plus G by 2. So just think of what has happened.
Tau plus and tau minus, I think it's going to
Perhaps correctly, but maybe so tau plus tau minus. I have taken them with root.
yeah.
Okay, sometimes people take them with 2. Okay, and then this take them with 2, then this G by 2 goes away and becomes G. But okay, so that's a matter of.
These two vertices will have different strengths and these two vertices will have different strengths. Because there is tau 3 involved and that tau plus and tau minus.
Okay, that is possible. So what is combination of tau 1 and tau 2? By 2. So let's correct that and next time I will correct this. It's 2, is it?
He cannot.
Okay, so maybe this is something else. Okay. But anyway, so yeah, this might give you a factor of root 2 here. Yeah. Yeah, so I will correct it the next time. Okay. But you can appreciate what has happened there. So we have managed to obtain all the vertices that are in this theory. However, what did we start with? I didn't tell you what the coupling constants were. All I told you is that this has some SU2 gate symmetry. The single statement was sufficient to tell you what the vertices were and what this coupling constants were. This is the strength of gate symmetry. Real gate symmetry, it tells you everything about all possible types. So this is where we had reached. So we had reached all the standard model Lagrangian terms with SU2 plus U. So at this point, as I mentioned yesterday, we don't have any masses. The gauge bosons don't have any mass, and the fermions don't have any mass. So therefore, now we'll see how we can get mass from this standard. Getting mass terms, the rule of thumb means getting a term that looks like B times B. So how do we try to figure out what are the mass terms? Okay, so before that, we should get familiar with this notation. So let me tell you what notation is. You already know what this means. So the two numbers that you see in brackets, the first number tells you about SU2. It tells you whether it's a doublet or a singlet. So whenever I have 2, it's a doublet. Whenever I have 1, it's a singlet. So this is a left-handed up type walk. It's a doublet at SU2. Similarly, down type walk, doublet at SU2. Then Right-handed quarks are singlets, there is one. Left-handed leptons are doublets, so there is two. Atomic electron is one, and Higgs is two, so that's doublet. SU2. What is the first one? The second number gives you hypercharge, weak hypercharge. That's Y. These are just Y values. 1/3 for left-handed quarks, 4/3 and -2/3 here, -1 for left-handed leptons, -2 for ER, and 1 for phi. That's given. Now what is our job? Our job is to find out which are terms that we can write in the Lagrange. Because finally we want to get our masses by writing some terms in the Lagrange. But we cannot write any terms in Lagrange. We have a constraint. Our constraint is that any term we write in the Lagrangian should be invariant under SU2 and U1. That we cannot assume. That is our sacrosanct. So what we have to do therefore is combine whichever way we can combine all these fields to get terms which don't change under SU2 and U1. So how do we see that? So let's look at both separately, SU2 and U1. So yes, let's not look at U1 because that is very simple. Okay, one thing to note is that you need renormalizable theories. Therefore, you cannot have many fields in the Lagrangian. Each term should have maximum dimension of 4. So if I write a term in the Lagrangian, each term should have a maximum dimension of 4. And this happens because you want to renormalize the dimension. Now we know that all the fermion fields have a dimension of fermion fields have a dimension of 3 halves, and all the bosons have a dimension of 1. So the way to see it is like this. Okay, look at Lagrangian of fermion. What is the kinetic term of fermion? So it's psi bar gamma mu I then mu psi. Now this is Lagrangian density. So this should have mass dimension of 4 because finally action is integral. So integral d4xl, which will be dimensionless. Lagrangian must have dimension of 4. Now we know that del mu, the derivative, has dimension 1. It's d by dx. So dimension of 1 over x, dimension of energy. So therefore, what is left with us is 3 dimensions of energy, or psi bar psi. Each of them should have dimension 3. So fermion is 3. Go to look at boson. Boson has something like del mu phi, del mu phi. Therefore, del mu also give you 2 dimensions of energy. So therefore, phi should also have 1 each. So therefore, phi will have dimension 1, and psi will have dimension 2. Therefore, all the Lagrangian terms that we will see essentially will have involve 2 fermions and 1 boson. 3 halves, 3 and 1 is the same. We can go back to this Lagrangian we have this problem. Last term. And we can actually try to look at dimensions of all the terms. And we will turn out that everything basically has dimension 4. This W mu nu, for example, has one derivative of W.
That is del mu b nu.
Del mu b nu, 1 over 2, and then multiply b mu b nu, so forth. So this has 4, this has 4. To look at this term, this is the L bar del mu L, so 3 halves, 1 and 3 halves, that's 4. This is again the same. halves, this W is 1 and this N is. So all terms are of this kind. All terms here you will find 2 fermions and 1 boson. For Higgs, phi has dimension 1. So it's mod squared. So phi 2 and then these will give you. So that's it. So everywhere you want dimension 4. And we will see that when we write down this V of phi, it will also be a dimension 4. So we want dimension 4.
All the dimensions should be equal to 4, not maximum 4. Earlier you have written maximum 4.
Okay. See, you can have, of course, you can have terms with dimensions more than 4, but then you have to write down constant in front of it, okay, which are dimensions 1 over mass. Okay. That's such things are problematic. Such things are not resolved. So people, you don't talk about such.
Each term should have dimension.
Each term should have dimension of 4. That's always true. Okay. Lagrangian has dimension of 4. Okay. You can always write Lagrangian with fields more than dimension 4, but then you need a coupling constant which compresses for dimension. So for example, see, I can always write my Lagrangian. I can write it as phi, 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 phi. The dimension 6. As long as I can write something which is 1 over m square, I'll just write 1 by m. So it's a perfectly good term to write as Lagrangian. However, if I have this term in my theory, I will have problems with inorganization. If I go to higher loads, I will get more and more infinity which I cannot control. So good theories therefore have coupling constants which are dimensionless. Okay. You can also have those which have dimensions of mass. Positive ones are okay, but negative ones are very very. They are non-inverse. Ones with positive, so if I get something, for example, this is not a real thing. Okay, maybe I give you an example. So one potential for Higgs, we have a term which looks like mu squared phi phi. That's okay. Positive dimension of coupling constant usually is okay. That's not right. But a negative dimension it's not. So if you don't know this, just take it as a rule of thumb. Okay, so where were we? So now, this is what we know. So we know that we can only write terms with that dimension 4. So we have a maximum 3 fields. Now, we need to check invariance under U1. Now, what does U1 do? Okay, let's say the Lagrangian has 3 objects. Okay, let me not differentiate fermion boson. We just write down everything as some notation. So let me write psi, but psi can be a boson. So let's say it is some psi 1, psi 2. 0. We know we cannot write 4. This it's only 4. So what does this mean? Under my U1 symmetry, this psi 1 will get a phase, which is e to the power some I g prime by 2 alpha times y of psi 1. The second becomes e power I g prime by 2 alpha y of psi 2 over I g prime by 2 alpha y of psi 2. Yeah, so this is operator, so let me write this because okay, so what will this become? So this basically becomes psi 1 multiplied by a phase which is e to the power I g prime by 2 alpha times y1. Okay, y1 is y of psi 1. Psi 2 will give me y2. Okay, so this will be y1 plus y2 plus psi 3 will give me y3 times psi 1 psi 2. And we want this to remain invariant under SU2. I'm sorry, under U1. What would that mean?
Sum of the terms.
So this term should become 1. So U1 implies that y1 plus y2 plus y3. So this tells you that if you want terms to be invariant under U1, this is what you should have. All your fields, take y's of all your fields, add them up, and they should become 0. So that's condition number 1. Now, let's go to invariance under SU2. A good thing to work is in terms of analogy with speed. SU2 is just speed. You are familiar with how speeds rotate and what happens. So now, if I take another thing, which is again I have a psi 1, psi 2, psi 3. Again, what I do is transform it under SU2. So this is e power I g by 2. What is it? Alpha bar dot tau psi 1 power I g by 2 psi 2. So these objects are nothing but rotations, spin half rotations. So all our SU2s can be looked upon as doublets can be looked upon as spin half objects with spin up and spin down. So in that rotation this is. So now what we want therefore is that these three objects when combined, so e power I by 2 alpha dot, this is tau 1 plus tau 2 plus tau 3. It's a back rotation. Yeah, back rotation. So let me call this thing alpha, beta, gamma. So alpha, beta, gamma. So tau alpha plus tau beta plus tau gamma. These three parts. So therefore, again psi alpha, psi. So what we want is the sum of these three should be equal to 0. So now you can look at the spin analogy to this. So this is like an object with spin given by tau. So if a doublet means spin half object. A singlet means spin 0 object. So if it's singlet, the value of tau is going to be 0. So now, for example, so what I want to look at is I would like to know the spin of this. This is the spin half object. This is a spin half object, and this is a spin 0 object. For example. Now the question is, can I make a combination of these three objects to make a spin 0 object? But I want power versus power versus power. So with half and half, you can actually combine them to make a spin 0 by taking the anti-symmetric combination. So it's possible. So therefore, it's possible to form a SU2 invariant object if I have the doublet, and singlet. I agree with this. So spin half, and 0 can form. However, if I have spin 0, spin half, and spin half, so 0, half, and 0, I cannot do this. Similarly, half, I cannot do this. Okay, and so on. This analogy will extend even if you go to spin 1. Okay, so at some point, not certain point, but you might have triplets. A spin 1 object. So it's possible to have a spin 1 object, a spin half object, and a spin half object, and combine them to make a spin less object. So another thing to think about is the following: look at these objects as spin objects and see if you can combine them to make spin. Yes. So there are two things you look at. You should take three fields, or more, such that if you sum over all the y's, you should get 0. And if you look at the spins of these three objects, they should combine to give the 0. This should be possible to do. So if you are able to find such terms, then you can write them the Lagrange.
When you say spin zero, you mean total spin zero.
Total spins. Not just
Spin
spin.
z.
So now you have these terms, and now you have been given all the doublet singlet or SU2s and Y quantum. So let's try to find out which are the combinations that we can have that can give us a 0, 0. Okay. Yeah, well, it turns out that there are not many such terms. Okay? Or both of these are other distinctive combinations. Only terms you can write, for example, looking at here, look at this term, it's easier to see. Let's say EL bar phi ER. So ER is 1 minus 2. Phi is 2, 1. And EL bar is minus 1. So it's down at this one. So let's look at a term which is EL bar times phi times ER. So EL bar is this. It was 2 minus 1. Therefore, EL bar is in the doublet, but it's EL bar. So Y becomes plus 1 because it's going up. If you look at phi, phi is also a doublet, residue, and its hypercharge is plus 1. ER, the singlet at the residue, and its hypercharge is minus 2. Okay. Now, first simple thing to check is that hypercharge addition can become 0. Plus 1, minus 2, that's 0. That's okay. Second thing to look at is this is a spin half. Yeah, this is spin half object. Spin isospin, big isospin space. Spin 0 object. Okay. So half of 0 is possible to make a signal. So therefore, this term can be SU2 crossover in and we can write terms. This is a simple rule of thumb. Just like an EL bar phi ER, we can also have terms which look like DL bar phi DR. So let's see what that term is. So DL is 2 1/3. So therefore DL bar is going to be 2 minus 1/3. Phi is 1 and DR is 1 minus 1. So Y matches and also the isospin addition matches. So you can have this. Another term you can have is what looks like UL bar phi conjugate or phi bar times UR. So UL bar the same as DL bar. So UL bar is 2 minus 1/3. Phi conjugate is the complex conjugate of phi. There are also SU2 rotations. Anyway, this is 2 minus 1. And UR is actually 1 4th. So Y matches and spins can match. So therefore I can write down these statements. Turns out that however much I try, I cannot write down any other terms. These combinations. You can see the restriction on the number of terms. 4. I have a restriction, right? Dimension should be 4, not number of terms. So dimension should be 4. Therefore, I cannot just simply write down many terms. So I should basically pick up some combinations of 2 or 3. So therefore, these are the only terms that you can write down. In principle, for example, you cannot write down a term which is a mass term for you. So let's look at these terms. See, all these terms are special because see, they are of the form some left-handed bar, phi, right-handed. Okay. So they basically look like En bar times, yeah, they are quadratic, like E, okay. And therefore they look like mass terms. So all the mass terms actually should always look like, so this perhaps mass terms always have to look like psi bar means psi r or psi r. Let me give you a very simple proof of this. So mass number from here should look like m psi bar psi. This you agree? Because dimension should be 4. Fermion has dimension of 3 halves. So therefore it has to look like m times psi bar psi. Okay. Now I write my psi as psi n plus psi r. You know what is psi n? Psi n. So psi n is 1 minus gamma phi by 2 times psi n. And psi r is 1 plus gamma phi. So this is often called as L. L psi. Not to be confused with the L's and R's here. So what does this become? So this I can write as M times psi L bar plus psi R bar times psi N plus psi. So this is M psi L bar psi L plus psi N bar psi R plus psi R psi L. Now look at this term, psi bar psi. So what is this term? So psi N is this. So psi N is 1 minus gamma phi by 2 times psi. What is psi N bar? Psi N bar is the complex conjugate, so Hermitian conjugate of this with plus a gamma 0. So then when I took bar, so psi bar will have the psi bar times 1 minus gamma phi by 2. 1 minus for psi dagger and then gamma 0. This psi dagger is gamma 0. This becomes transpose, not bar. So this becomes psi transpose. When this gamma 0 passes through this gamma phi, it gets a negative sign. So this psi dagger gamma 0, but now this becomes 1 plus gamma phi by 2, 1 minus gamma phi by 2 times psi. Okay. And this is 0.
I think gamma 0 then any complex liquid of 1 plus 1 because I
I'm not sure.
complex liquid
Yeah. But gamma 2 also has
then those gamma themselves will change. So you have to, if you want to write it like a then you'll have to multiply again and see what it does.
Gamma 2 has I. No, the problem is I.
no gamma 5 is equal to I times gamma 0 gamma 1 gamma 2.
Okay, yes.
Then taking complex liquid I will become minus I. Then it should be
Remember, However, gamma 2 which is inside this was also an I. So all those ions will change. So there are two ions which change sign.
Okay.
So gamma phi stays gamma. So all the gamma and gamma, all the psi n bar psi n terms are always 0 by definition. Similarly, psi r by psi r terms are always 0. So mass term, although you write as m psi bar psi, it basically means m times psi h bar psi r plus psi r bar psi. So in fact that is what we had in our all the terms that we wrote down. All of this form. Okay, so if you take out this file, this looks like ul bar ur. And similarly there is summation conjugate which is ur bar ul. So let's calculate down. So mass for electron. So we have a term which is En bar phi er. You can have a complex conjugate term. So you can have ER bar, okay, phi star, okay. And at some point of time when Higgs gets vacuum expression value, it will come. There is a constant here. The constant is, let's say, lambda E. When phi gets vacuum expression value equal to V, then this is going to become lambda E V. Okay, so this is lambda star. And then E bar ER plus lambda star V. So this is going to give you mass term for E. So all these terms are usually written as, let me go back to the direction that we okay. So look at this term. So lambda n bar phi r. N is definite part, r is alternate part of the same field as the phi. Okay. Only such things are given. And these terms will finally give masses to the electrons, muons now, uptime box and downtype box. Okay, the reason is the following. I will come to that. The reason is that this term will only give masses to d type box, and this term will only give masses to u type box. So electron is so strictly speaking, when I say downtype clock, it means T3 equal to minus above. So low.
Yeah, that's what I was asking. Whether it means all.
Yeah. So
Isospin.
all isospin minus above. Yes, that is all isospin. And it happens because the vacuum expression value of Higgs is only 1. So in general, this is how fermions will get to us. So we'll come to that. So till now we have got no mass connection. All we had was mass connection. Then we'll go to this other problem before we come to neutrino, which is giving mass to gauge bosons. So indicate to how we get. I told you yesterday that it's a sacrilege to give mass to gauge bosons directly. You can't write n square BB kind of because gauge symmetry is good. Never. So therefore we have this mechanism called electroweak symmetry. So what happens? In the Lagrangian, you are not allowed to break the symmetry. So theory goes. It's okay if you break the symmetry as initial conditions. This is the symmetry breaking. Right? So Lagrangian obeys the symmetry completely, but your initial conditions break the symmetry. That's okay. That doesn't create give you problems with your loops, because loops only involve your particles. Lagrangian. It doesn't involve conditions. It's okay. In speaking parlance, it says that your vacuum may break the symmetry. It's okay. But your dynamic should not break the symmetry. So Lagrangian should be constant. Vacuum is okay. Whichever vacuum is given to you to start with, then you start with that. So this electrolytic symmetric vacuum mechanism or the Higgs mechanism, basically that which is able to give you. So for that, one has to start with the potential for Higgs. So idea is the potential for Higgs is such that the vacuum is not symmetric. So this is the potential that is given. So mu square times L mu phi dagger L mu phi. Oh, sorry. Sorry. It's a wrong. Mu square phi dagger. So potentials is derivative part already came in the Lagrangian dynamic. Okay, so mu square phi dagger phi plus lambda times phi dagger phi square. It's a term that we can write because phi has dimension 1. So 4 phi are okay. So you can write on this term. Now you might have looked at this Higgs potential in pictures. So that usually is a one-dimensional thing. This is a four-dimensional thing because the phi is actually two complex numbers, phi plus and phi 0. Okay, so upstairs is phi 1 plus I phi 2, here is phi 3 plus I phi. However, the idea is the same. So if you are going to draw the potential d phi, it basically, I cannot write it's a four-dimensional thing, but it is like a Mexican cat thing. So it cannot exactly be drawn. One dimension analog if you look like this. Okay. But of course this phi is this phi which can be in any direction. So let's see what happens. If mu square is positive and lambda is positive, then of course minimum is at phi is equal to 0. And that obeys the symmetry. So this is fine. However, if mu square is negative, then what happens? Your V phi then gets this Mexican shape form. So this is mu square less than 0. Then it means that the minimum is not here, but the minimum is somewhere here. So I can take derivatives of this. So I find the minimum of this phi. So V is equal to mu square phi dagger phi plus lambda square. So if I take V prime, let's say take this phi dagger, then I get mu square phi plus lambda phi dagger phi times phi. So if I want this to be equal to 0, my mu square by 2 lambda should be equal to phi dagger phi. So it implies V A at phi dagger phi equal to minus mu square by 2 lambda. It is similar to what we had in the case of simple vacuum. Okay, so this is the condition. So what is this condition? If I see what is phi dagger phi in this state, it's actually phi 1 square plus phi 2 square plus phi 3 square plus phi 4 square. So what I have been given is this quantity. So take this 3 scale. So phi 1 square plus phi 2 square plus phi 3 square phi 4 square equal to constant. So that's 3 scales. It's a sphere in 4 dimensions. The surface is 3 dimensional, so it's called 3 scale. So only phi 1, phi 2 would be a circle. So circle is called as a 1 square. 3, then it becomes one sphere, two sphere, three sphere. So therefore, if I am anywhere on this sphere, I can satisfy this condition. And nothing is given, there's no way to choose where to. But at some point symmetry has to be broken because you have to go to some one vacuum. And in principle you can go anywhere. Depending on where you are, you will have different physical consequences. I tell to you that we make a symmetry in this particular manner. Take the symmetry like this. We choose a point on this sphere, okay, which has phi1 equal to 0, phi2 equal to 0, phi4 equal to 0, and phi3 equal to 3. Okay. So let's say we choose this point, and now we'll see what are the consequences. You have to choose some point, therefore we chose this. So now we see what has happened. Therefore, our phi here, instead of having 4 different degrees of freedom, has only 1 degree of freedom. Near the minimum, its value is equal to v. But near the minimum, it can also oscillate. So this is the field which is written as h. It's a real field. And this field is what its value is in vacuum. There are no other fields. The value of Higgs field is 0 v. Yes. So there is no dynamics. Higgs will just be 0 and v. So that's the vacuum. So go back and try to imagine your Lagrangian. So now we're talking about Lagrangian without any fermions, without any gauge boson, only Higgs. And then what happens is the Higgs value is 0 v. So what does this mean? Inside my vacuum, now I have got an object that looks like 0 v. So this is basic, right? So this is in vacuum. So this phi always exists. Now what does this mean? See, this phi is not any arbitrary object. It has SU2 charge, it has U1 charge. It has T3 equal to minus half. Now if you tell me that inside vacuum, I have some object V, some value V, which is equal to minus half, then I am in trouble. Right? So it means that inside vacuum I have a T3 equal to minus half object, which means even if there were no other fields present, I will have a T3 equal to minus half object. Which is what I mean by breaking the SU2 cross U1 symmetry in vacuum. So vacuum break SU2 cross U1 symmetry. In the vacuum, you only have Higgs field which is 0 v. So this has definitely broken SU2 cross U1. It has broken U1 because T3 of this field is minus half. Okay. So basically, it means in vacuum you have a T3 equal to minus half field every time. So you have broken U1 symmetry. Secondly, this Higgs field is a SU2 doublet. And this V is at T3 equal to, I have mentioned T3 equal to minus 1, sorry. And this field has Y is equal to 1. So this object V, which is there throughout in vacuum, has Y is equal to 1. So in vacuum everywhere you already have Y is equal to 1 without having any other fields at all. No particles, but V is equal to, Y is equal to 1. So therefore, what we have done is we have broken SU2 because T3 is not conserved. We have broken U1 because Y is not in vacuum. What we have not broken is the combination that looks like T3 plus Y. Because if I take T3 plus Y by 2, if I take T3 and Y by 2, it's equal to 0. So inside the vacuum, I have T3, I have this V everywhere. Okay. But even if I have V everywhere, I do not break T3 plus Y by 2. It's some object which I know is not broken. Although if I break SU2 and U1 both sides. So what have we done? Lagrangian does not break SU2 or U1. So Lagrangian does not break SU2 cross U1. Vacuum breaks SU2 cross U1. But it does not break something that looks like T3 plus. What does this mean? If you look at your complete theory, okay, after all this breaking, if you do experiments today, you will find that SU2 will be broken. So if you try to find some interaction, there will be some interaction that will break SU2. There will be some interaction that will break U1Y. However, everything that you will discover in experiments will conserve T3 plus Y. So although we have broken all these symmetries by Higgs, we were unable to break this symmetry. This object is actually called as Q and is electric charge. So electric charge is that quantity which vacuum cannot break. If vacuum had broken it, you would have found the world full of positive charge. So what did we do? We broke our SU2 plus U1 symmetry in such a way that an object was conserved. That object was. So this goes back to why I chose this particular combination. If I had chosen some other combination, configuration would be different. Right? If I had chosen phi1 to be non-zero, then I would have had positively charged objects everywhere in that. And I know that doesn't happen. So therefore there is a particular choice of phi1, phi2, phi3, phi4 which works in our case. The reason we chose this combination was because I knew that if I chose this combination, I will conserve electric charge. So all these things are interconnected. Okay, so there is not much freedom for me. Once I choose my gauge symmetry, SU2 U1, even if I want to break it, I cannot break it in any way I want. There is only one way I can break it, so that I can be consistent with all the experiments. So therefore, this is conserved by vacuum. And in Zamiga field theory, write this thing like this. So your symmetry of SU2 cross U1, it got broken to U1Q. And you know what is U1Q? Right? This you have written many times in electronics. U1Q basically means that if you have field psi, you can go to e to the power I alpha Q. So now all comes back to what we do. So basically what we did now is design electromagnetism starting from SU2 plus U. So if you haven't seen this before, it perhaps makes sense for you to go back and try to see what. Next thing we are going to try to see how gauge goes on meter mass, but it's rather late now, so I will stop at this point of time. Okay. So the part that I have shown you till now is very important, and we will give similar arguments in the next class to give neutrinos masses. So therefore, just go through this carefully by the time you come for the next class. And And then in the next class we start with giving masses to gates bosons, and then we will give masses to